Table lunch is going to be on how Major League Baseball creates schedules and how much is offense worth relative to defense. The last homework assignment is due today. There is no more written homework. That does not mean you shouldn't be doing math problems. It means you should be choosing the problems to do. If you do not have any problems, I will give them to you in whatever way you want to interpret that. I will help you find what you should be looking at, okay? That's how you should be using the time. The first part of the exam is going to be on Friday in class. Part of it you can do at home. Okay, so the purpose of today is to squeeze 2 weeks of material into one day. The reason is I want to be able to do things like applications, and we only have 12 weeks. Path to Green's theorem. So the goal is to generalize the fundamental theorem of calculus. All right? So the fundamental theorem of calculus states the area under a curve is related to the antiderivative at b minus the antiderivative at a. So I want to give you a sense of what's going on. So we have the integral from a to b, and I'm going to write it like this, of big F prime of t dt is f of b minus f of a. Or another way of writing this is the integral over ab of df is f evaluated at the boundary of AB. Okay. Another way of writing this is the integral over AB of df is the integral of f over dAB, where I'm using the partial to denote boundary. So essentially what the fundamental theorem of calculus is saying is the integral of the derivative of a function over a region is the integral of the function over the boundary of the region. Now in one dimension, imagine I want a closed curve. So I have to stop and start at the same point, or start and stop at the same point. What kind of paths can I have in one dimension where I start and stop at the same point? Okay, I can go forward, someone said, and then come back. But when you integrate, if you go forward and you go back, they cancel. So effectively, there's only one path in one dimension where you start and stop at the same point. Nope, not a circle. Well, it's a circle of radius 0, a point. So the only closed path in one dimension is a point. Wow. If I let a equal b, what we're saying is the integral of f from a to a is 0. All right? The fundamental theorem of calculus is not that impressive if I'm integrating over a point. But we'll see the generalization is. So let's start the path to Green's theorem. So the first is arc length. So we have a curve C of t in R3. And so by a curve, I mean the following. I have some interval AB, and I have a map C, which takes points in AB and gives me points in three-dimensional space. So for example, here's a nice one. C of t is cosine t, sine of t, t. And if you think about what's going on, you give me a value of t, and this tells you where I am. If I didn't have the t here, if I just had a 0 there, I would be going in a circle about the plane. But because I have a t here, my circle, as I draw it, I keep rising my finger, and it's going to trace out a helix. How many dimensions is a curve? Is it 1 dimension, 2 dimension, 3 dimensions? It lives in three-dimensional space, but how many dimensions is a curve? It's not 2. 1. How many values, how many inputs do I need to know where I am on the curve? I just need to know one value. I need to know t. This is like a line. If I give you one value on a line, if I give you t, you know exactly where you are. On a plane, how many inputs do you need to specify where you are on the plane? 2. And so curves are one-dimensional objects. Okay, one-dimensional objects. We don't have time for sneezing today. All right, C prime of t, well, let's see, if C of t more generally is x of t, y of t, z of t, then C prime of t is we just take derivatives component by component. It's x prime of t, y prime of t, z prime of t. All right? And so now I'm going to claim the following. Claim the length of the curve from A to B is the integral from A to B of the length of C prime of t dt. And so if I expand this out, I would get the integral from A to B of the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. Is this a Calc 3 problem? What class does this live in? Calc 2. And it's typically a hard Calc 2 problem. Why do you expect this is going to be hard? Why do you think in general these integrals will be difficult? Yeah, because there's a square root. So in general, arc length is very hard. If you want a great challenge, try to calculate the length of an ellipse. It turns out to be surprisingly difficult to write down the length of the ellipse, even though the area is very easy to get. All right, so when you see a formula like this, you should ask, well, why is this true? So let's imagine I have my curve C of t. So here is a proof. All right, and so what I'm going to do is here's my interval AB, and I'm going to chop it up into lots of pieces. And so here's ti plus 1, and this distance I'll call delta t, ti plus 1 minus ti, and let's say all the pieces are the same size. I'll chop it up into n pieces. What does this look like? Where have we seen this before? Riemann sums. So this is going to be a great way to review Riemann sums. So let's take, here's the point C of ti. Here's the point C of ti plus 1. I want to find the length of the curve from here to here. I'm going to approximate it by drawing the straight line over here. Do you think this does a good job approximating the length of the curve? If not, what could I do to make it a better approximation? What should I increase? Increase the number of points I use. As I take more and more points, the polygonal approximation will become better and better and better. And so right now, if I don't have too many points, if I just have a couple of points like this, but as I start taking more and more points, I would then replace this. I would place this. And it should get better and better and better. And in the limit, I should get the length of the curve. So these polygonal segments in the limit, when summed, will give me the length of the curve. So what is C of ti plus 1 minus C of ti? Well, it's x of ti plus 1 minus x of ti. We only have a day, so I'm going to just write blah for y and blah for z. Okay? How can I approximate x of ti plus 1 minus x of ti? What theorem should I use? I'm sorry? Mean value, right? When in doubt, mean value. Right? I love this theorem. Right? This is going to just be x prime at some point, let's call it ui, times delta t. And then here I'll get y prime. It may not be the same point, so I'll call it vi delta t. And then z prime at some point, delta t. Okay? And so that's going to be the difference between cti plus 1 and c of ti. And now, if I sum, I goes from 0 to n minus 1 of c of ti plus 1 minus c of ti. This is going to be the sum. I goes from 0 to n minus 1. All of these have a delta t. And then I just need, I want the length of these vectors, so I put in the length symbol. So how do I take the length of a vector? It's the square root of the sum of the squares of the components. So I'll have the square root of x prime of ui squared plus y prime of vi squared plus z prime of wi squared delta t. And now we take the limit as n goes to infinity. Let n go to infinity. And this will converge to the integral from a to b of the length of c prime of t dt. Okay? So this gives me ways of integrating and finding the length of the curve. Now the problem is, in general, these integrals are going to be extremely difficult to do. Okay. So now the next thing is to do an example. Right? What would be a good curve to take? Well, let's try c of t is cosine of t, sine of t, t. So what would c prime of t equal? Derivative of cosine is negative sine of t. Derivative of sine is cosine of t, and derivative of t is 1. So the length of c prime of t would be the square root of minus sine of t squared plus cosine of t squared plus 1. What does this quantity equal? Radical 2, square root of 2. This is one of the reasons why I like the helix, because in the helix the square root is actually nice. Okay? In general, it's going to be hard, but you could actually figure out very easily what is the length of a helix. Now the other thing is, you might want to do more with a curve than just calculate the length. So what you might want to do is, maybe you have a density and you want to figure out what is the mass of the curve. And so maybe the curve weighs more in the beginning and weighs less in the end. Well, if you think about what we're doing, it's not that hard to integrate a function over a curve. And the reason is, I break up the curve into these polygonal pieces. Will the value of my function change that much over a short polygonal piece? Will it change a lot from here to here? Quite possibly, yes. From here to here? No. So if my pieces are really close to each other, then I don't expect there to be that much of a change. I can go through the same argument here, and instead of having just the length of c of ti plus 1 minus c of ti, I could multiply this by f of ci. And that would give me the integral of f over curve. So we call these, let me make sure I do these right, path integrals. So integrate a function over a curve. And so we'll write the integral of f over c ds. And so ds is going to mean an infinitesimal movement. This is going to be the integral from a to b of f of c of t times the length of c prime of t dt. Okay? And so now all I have to do is figure out what is f, figure out what is c prime, calculate its length. What kind of problem have I reduced this to? Is this a Calc 3 problem? It's Calc 2 again. So the Calc 3 is in parametrizing the curve, is in calculating the length of c prime of t. Once you reach this point, it's now a Calc 2 problem. So for example, if c of t is again cosine t, sine of t, t, because I don't have time to take another derivative, and f of x, y, z is x plus y plus z, then the integral over c of f ds would be the integral from a to b. Now, x is going to be cosine of t, y is going to be sine of t, z is going to be t. So we'll get cosine t, well, I'll do it slowly. We'll have f of c of t, the length of c prime of t dt. So it's the integral from a to b, f of c of t, so f of cosine of t, sine of t, t. What was the length of c prime of t? Square root of 2, which is nice, dt. And now we integrate from a to b cosine of t plus sine of t plus t times square root of 2 dt. And so this is how you would do path integrals. path integrals are not that bad. Okay, so doing this allowed us to review the mean value theorem. It allowed us to review Riemann sums. It allowed us to review a little bit about our stuff on vectors. Okay, so the next thing we want to do is we want to generalize this. So rather than integrating a function over a curve, what else could we integrate? So what's another object we could study? So rather than integrating a function, what could we integrate? A vector. So most of you will never use Green's theorem or any of this ever again in the rest of your life. I apologize for my brutal honesty. Right? But what you will use is how do you look at something in life and try to extract what is worth studying. There are many things I can study, and there are many ways to define the integral of a function over a curve, especially the integral of a vector over a curve. I want to try to justify to you why this is worth studying. So line integrals. So we have a curve C of t, and then we have a vector valued function f of t is f1 of t, f2 of t, f3 of t. And I have some curve in space. Given any point on the curve, there's a couple of natural directions attached to that point. Can somebody give me a natural direction attached to the curve at that point? So I'm traveling my curve from here to here. At this point, what's a natural direction associated to that point? The tangent. So here's the tangent. What's another natural direction? The normal. Now it turns out there's infinitely many normals. So I give you some curve in 3 space. At this point, all of these directions are equally valued as the normal. But there's only one tangent. So the tangent is uniquely defined. It's a unique direction. So I hope you're now adequately primed. Which do you think we should do? Integrate this with respect to the tangent or with respect to the normal? The tangent. So now, how can I get a number from f of t and c prime of t, which is the tangent, x of t, y of t, z of t? I want to somehow get a number from these. If I wanted to get a vector, if I just wanted to integrate the vector over the curve, I could integrate it component by component, and then that would just be 3 path integrals. So if I want to get a vector valued answer, I know how to do this. Just do 3 path integrals. I want to get a number. You should think of the interpretation of as what's going on is you're traveling on some path. Maybe here is the sun. We don't have time to make it in color. And you're being pulled towards the sun at each point. And you want to figure out how much work is done on you as you travel. So this is where a first course in physics would be very helpful. I have some force. I want to figure out what work is being done by the forces. Okay, so I want to get a number. How can I get a number from these 2 quantities? Dot product. So we're going to study the integral over c of f dot ds. And I now put an arrow over the s to remind myself that this is a vector. And this is going to be the integral from a to b of f of c of t dotted with c prime of t dt. So why am I evaluating f at c of t? Why am I not evaluating it at t? It's not an accident. I'm sorry? Like, okay, so I am, good point. I'm actually abusing notation a little bit. ds just means the infinitesimal motion in here. So actually that was a good catch. I'm abusing notation a little bit. So abusing notation. This is one of the problems in having only one day. When I write f of t, I really have to be very careful now because here f has 1 input, here f has 3 inputs. So this is really a bit of an abuse of notation. I do apologize for the abuse of notation. It's standard to abuse you this way. What am I trying to do? I'm trying to integrate a vector valued function over a curve. So if I'm going to try to integrate a vector valued function over the curve, where should I be evaluating the vector function? At the curve. What does this remind you of? Where have we seen something like this before? We've got to be very careful where we evaluated things. So the directional derivatives, but something else, the chain rule. It's very easy when you're doing the chain rule to forget where to evaluate things. Or when you have the tangent plane, you have to remember where do you evaluate the partials. So we want to be on the curve. And so this is really what we mean. So this is our integral. All right, so what does this mean? So we have the integral from a to b of f of c of t dotted with c prime of t dt. I'm going to write this out in its full glory. This will be f1 of c of t times x prime of t. I'm just doing the dot product, plus f2 c of t y prime of t plus f3 c of t z prime of t. And then I have a dt. All right? So if I just take the dot product of c prime of t with f of c of t, this is what I get. Can someone tell me another way to write x prime of t? What's another notation for x prime of t? So in Calc 1, you have the prime notation from Newton, but you also have notation from Leibniz. How else would you write x prime of t? How else would you write the derivative of x with respect to t? dx dt. So this is the same as dx dt. This is the same as dy dt. And this is the same as dz dt. As an aside, I want to calculate the limit as n goes to infinity of the sine of x over n. I'm not telling you what x is, but what's the range for the numerator? Sine of x lives between what and what? Negative 1 and 1. And what happens to the denominator as n gets large? So as n goes to infinity, what happens to the denominator? Does it get large or small? Large. So what is the limit as n goes to infinity of sine of x over n, no matter what x I put in? Sorry? What was it? Not one person can calculate this limit? 6, right? All right, I'll show the steps. Right? Right? Can I do this? Math should be independent of the language. See? Da? Kane? Right? dx dt times dt. What's dx dt times dt? dx dt times dt is dx. So I will continue, and I will write this as the integral from a to b of f1 dx plus f2 dy plus f3 dz. If you're bothered by this, don't go into economics or physics. Take more math classes. We will justify this eventually over time. This is the power of the notation. The dx dt times dt is suggestive, but this is really a notational leap. Notation. All right? You've got to be very careful. You can't just cancel the dt's. This means the derivative of x with respect to t. Okay? But as a notation, this is a really good idea, a really good way to kind of convey what we're trying to do. Okay, so this gives us ways to calculate line integrals. And it turns out in physics, this is a very important thing to study. I want to do a very special example. I want to integrate from a to b of the gradient of f at c of t dotted with c prime of t dt. Okay? It turns out this is a very important thing to study. If you have things in physics like forces, the gradient is often related to the potential. This is related to the work done. All right, I'm going to introduce a new function. Let's let big F of t be f of c of t. How do I take the derivative of big F of t? This is a Calc 1 problem. It's a function of t. So its derivative is f prime of t. How do I take the derivative of f of c of t? Chain. Whenever you hear the word of, you should always be thinking chain rule. F of c of t. So this is going to be the derivative of f, which is the gradient of f at c of t. And so you can see all the great things we're reviewing dotted with c prime of t. Aha! That's exactly what we have here. It's not a coincidence. This is why I wanted to integrate this. What do we get? This is just equal to the integral from a to b, big F prime of t dt. I can't give you an easier integral. What's the integral of the derivative of big F? F. So you just get f of b minus f of a, or f, big F at b is f of c of b minus f of c of a. This is really nice. What it tells you is this integral over the curve only weakly depends on the curve. It just depends on where the curve starts and stops. So if here's my point c of a, and here's my point c of b, then these two paths, the integral of big F over those two paths is the same. I get the same value going from here to here like this as going from here to here. Okay, here's the fun part. Let's go from here to here, and then let's come back to where we started. So if I consider this massive curve, my starting point and my ending point are the same. If my starting point and my ending point is the same, what's the integral? 0. This is the generalization of, in one dimension, the integral over a point is 0. Well, in one dimension, the integral over a point is 0 is not that impressive. But here, this tells me if I have a very special function, then the integral of that function is independent of the path. And if I integrate over a closed path, I always get 0. So this is a really nice generalization of the fundamental theorem of calculus. It reviews a lot of good things. Another good example is let's take big F of c of t to be c prime of t divided by the length of c prime of t. So if I take a vector and I divide it by its length, what's the length of this vector now? It's a unit vector. So this is a unit vector in the direction of the tangent. So we're going to review some stuff from chapter 11 now. So now if I look at the integral over c of f dotted with ds, this is the integral from a to b of c prime of t over the length of c prime of t dotted with c prime of t dt. Well, what's c prime of t dotted with c prime of t? So if I give you a vector, what's v dot v? Not quite v squared, close. Something related to v squared. So this would be v1 squared plus v2 squared plus v3 squared. That's the length of v squared. So this is just the integral from a to b of the length of c prime of t squared over the length of c prime of t dt. Oh, well, that's just the integral from a to b of c prime of t dt. This is the length of c. So we can recover the length by doing a line integral. So we can get back to what we cared about by just looking at very special line integrals. OK, we have time for about 1 minute of questions. Any questions about what we've done up to now? We've done a lot. Right? We've talked about what it means to parameterize a curve. So you give me a point in time, and I'll give you a point in space. So a curve is this one-dimensional object, and as the time passes, I sweep out some curve in space. We talked about how to calculate lengths of curves. The way you calculate lengths of curves, unfortunately, involves integrating a square root. Integrating square roots is typically painful. But it's a Calc 2 pain, so it's not my department. Right? We then talked about, well, what if I don't want to just find the length of a curve? What if I want to weight the curve by some function f? We can do that. And those are path integrals. And again, we get these almost the same way by using Riemann sums. Then the question was, how would we calculate a vector integral? There's lots of different ways of interpreting what that should be. The most natural is each curve at any moment on it has a unique tangent direction as we continue. So a great thing to do is to look at the dot product of your vector valued function and the tangent. And so we saw that this led to line integrals. We saw the line integrals could recover things. We saw the power of notation. You, of course, have to be careful in just canceling symbols. There is mathematical rigor to justify this, but it suggests why some notation is better than others. This is the advantage of the dx dt notation over the x prime notation. It's meant to be suggestive. Okay, any questions on what we've done up till now? Okay, so now it is time to do Green's theorem. Okay, if you had your choice, what region would you love to integrate over? Nobody has any preference? Square, after a square. Circle. What do these two regions have in common? What kind of regions are they? They're simple. So now in our class, simple actually has meaning. So we want a simple region is horizontally simple and vertically simple. So we will do Green's theorem for simple regions first. So Green's theorem. Let D be a simple region with boundary curve C oriented counterclockwise. Mathematicians always do things counterclockwise. So for square, we travel the square like this. For a circle, we travel the circle like this. Okay. Consider f of xy is p of xy, q of xy, 0. I'm sorry. Just p of xy, q of xy. Okay. So I have some function of two variables. Then, and this is Green's theorem, the integral over my curve C of p dx plus q dy is equal to the integral over the region D of dq dx minus dp dy dx dy. So this is the statement of Green's theorem. It converts a two-dimensional integral to a one-dimensional integral. And it turns out that these two functions are related. Remember how in one dimension we showed that the integral of df over an interval is related to the integral of f over the boundary? This is the boundary of the curve D. So this is boundary of D. And if this is my function, it turns out this is the derivative of my function. So there's many ways to take derivatives of functions in several variables. dq dx minus dp dy does not look that familiar to you. It turns out it's related to things you've seen. This is called the curl of f. And I'm going to give you some motivation for where it is. I'm going to extend my function to be a function of three components. P of xy, q of xy, 0. So there's no z dependence, and the third component is always 0. So this always gives me outputs in the plane. Okay? I'm going to look at the cross product of the gradient operator and f. So this is a little silly what I'm about to do. I'm not quite allowed to do this. This is not a legitimate matrix determinant. I start off with the vectors I hat, j hat, k hat. I'm supposed to be putting in numbers when I do determinants. I'm going to continue doing illegal things, and after putting in numbers, putting in vectors instead of numbers, I'm now going to put differential operators, d by dx, d by dy, d by dz. And now I'll do something legal, why not, p, q, 0. And I'll take the determinant. All right? Well, we talked about how to calculate determinants. So we have I, j d by dx, d by dy, p, and q. So we go I, d by dy of 0. What's d by dy of 0? And then we would have j d by dz of p. What's d by dz of p? Does p have any z dependence? 0. K hat d by dx of q. Hey, that actually survives. So we have k hat dq dx. Now we have the negatives. And instead of going like this, I'm going to be careful. I'm going to go this way. We'll have k hat d by dy of p minus dp dy. Now I'll have I hat d by dz of q. What's d by dz of q? 0. And then I'll have j hat d by dx of 0. So notice, oh, dq dx minus dp dy. Hey, that's exactly what we have over here. So this is called the curl. This is just a convenient way of writing down what we're having. And so what we really have is we have the integral over c of f dot ds is equal to the integral over the region D of the curl of f dotted with, I'm going to write k hat ds. Because this vector is in the k direction. If I give you a region in the plane, what direction is the normal to a region in the plane? So I give you a region in the plane, what direction is the normal? Perpendicular in which direction? So I give you a region in the xy plane, which direction does the normal point? In the z direction or in the k direction. So when I do del cross f, its only non-zero component is in the z direction. And if I look at my region in the plane, its normal is pointing in the z direction. So I can write this a little bit more generally as the integral over c of f dot ds is equal to the integral over d of del cross f dotted with ds. And this is called Stokes theorem. And this is a nice generalization of Green's theorem. It turns out this is true even if you're not in a plane. So this is probably the first prop I've ever made for any of my math classes. My first year of graduate study at Princeton. Very expensive, has held up though fairly well over the years. Some fresh tape from today. This is actually Stokes theorem. I'm going to show you all the integrals you can now do. The coat hanger, I hope you will agree, is fixed. And as I move my hand inside the bag, is the coat hanger changing? All of these surfaces have the same boundary curve. So as I keep doing like this, am I changing my boundary curve? No. All of these integrals are the same. So if I ask you to integrate a certain function over the blue bag, it's actually the same as integrating over this circle down here of a related quantity. This is the power of Stokes' theorem. It reduces these incredibly difficult multidimensional integrals to a very simple line integral, to a very simple one-dimensional integral. All right, so now the question is, how do you prove Green's theorem? So what I'm going to do is I'm going to prove Green's theorem in the plane. I'm not going to bother with Stokes' theorem. And I'm going to prove Green's theorem first for the nicest possible shape. We have two candidates on the board. Which shape should I do, circle or square? Square. Why? Well, so we only use polar when we have circular symmetry. I have dx's and dy's. This is strongly suggestive of squares rather than circles. The other thing is squares fit together nicely without any gaps. Circles don't. And so what we can do is we can partition a general region into squares. This should remind you of how we did Riemann sums for double integrals. We take our region and we chop it up into squares, and in each square we look at where's the function largest, where the function is smallest. So again, we're reviewing so much of the semester today. So proof of Green for a square. All right, so it's very important to draw a good square. And so here are my four paths, 1, 2, 3, and 4, just so we can give the sides names. And let me give these points names. This will be the point AC. This will be the point BC. This will be the point BD. And this will be the point AD. All right. So these are the points of my square. And what I want to do is I want to calculate the integral of p dx plus the integral of q dy. So we need to show the integral of p dx plus the integral of q dy. Let me draw a better d there. Equals the integral over d of dq dx minus dp dy dx dy. So what I will do is I will calculate the integral of p dx. I will leave the integral of q dy as a very similar calculation. So let's calculate the integral over c of p dx. So on these 4 segments, 2 segments are very easy to integrate p over, or to integrate p dx. Where is dx particularly nice? Where is there no change in x? Which ones? Sides 2 and sides 4. There's no change in x. Now what we're doing here is we're basically using the econ physics trick of saying dx dt dt is just dx. If we had 2 weeks, I would do this slowly. I would write it out with f of c of t and do all of that stuff. We don't have the time, so I'm going to just say, look, dx is 0 along 2, dx is 0 along 4. And this is the same as the integral over 1 of p dx plus the integral over 3, nope, the integral over 3 of p dx. Okay, what is the range of x on 1? So in 1, what's the range of x? A to b. And now, what's the value of y along 1? Always equal to c. Now, what's the range of x on 3? B to d. Because remember, we're mathematicians today. We go around counterclockwise. So we start at BD and we end at AD. So x starts at B and ends at A. We're traveling the curve backwards. So here, and I'll write x equals A to just really remind myself. X equals B to A. And now what's the value of y? D. Okay. Well, how can I make this the same as that? Well, I just switch the order of integration. That costs me a minus sign. So this is the same as the integral x goes from a to b of p of xc minus p of xd dx. But I don't like how that looks. So I'm going to pull out a minus sign. Integral x goes from a to b of p of xd minus p of xc dx. We are 1 step away from the proof of Green's theorem. So I wanted to write it in this way because it's suggestive. I have this function p, and I evaluate the y component at d, and then I subtract off the y component at c. What does this remind you of? Good try, but no. Fundamental theorem of calculus. It looks like I'm evaluating a function. So what function am I evaluating? I'm evaluating the function p at d, and I'm subtracting it off at c. So I had to integrate to get here. It's the y component that I'm evaluating at. So what function did I have to integrate to get to this? So the answer is hidden on the board in what we're trying to prove it equals. dp dy. This is the same as the integral from x goes from a to b, the integral y goes from c to d, the derivative of p with respect to y at xy dy dx. Because if I integrate dp dy with respect to y, I just get p. I then evaluate at d, and then I subtract off at c. Well, is dy dx different than dx dy? This is a nice simple region. I can switch the orders. So I get, this implies the integral of p dx over my region C is equal to the integral over the region D of negative dp dy dx dy. That's half of green, right? The integral of p dx is negative p dp dy. So all I have to do now is show the integral over C of q dy is the double integral over D of dq dx dx dy. And it's a very similar calculation to show that. And this is a proof of Green's theorem. Well, it's a proof of Green's theorem in what region? Squares. So now what I'm going to show you is every region is a square. All right, every region is clearly not a square. Every region, however, can be written as a union of squares. Okay, so before I prove the squareness or the square decomposition, any questions on what we've done up till now? So this reviewed multivariable calculus, it reviewed integration, it reviewed simple regions, it reviewed Fubini's theorem when we can switch the order of integration. A lot of nice stuff was reviewed here. All right, so general case of Green's theorem. Yada, 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 yada. Okay. All right, hopefully everybody agrees this is not a simple region. All right, I'm going to show you how to prove Green's theorem in this region if you know Green's theorem for rectangles. So what we're going to do is we're going to chop it up into lots of little itty bitty squares and rectangles. And in each rectangle, do we know Green's theorem? Yes. So I'm not going to draw things to scale. Let's look at some huge chops over here. You know, I would never do this, anything this large in practice, but let's take something large like this. So now, I'll write down my orientation. So I go through, and I have Green's theorem on this rectangle. Now let's do Green's theorem on this rectangle. And now you're about to notice the miracle. What do you notice? What happens? The side that share cancels. In this side, in one rectangle, I integrate going in this direction. In the other one, I integrate going in the opposite direction. If you go in the opposite direction, you switch the value of the integral by a minus sign. These cancel. And so what this tells us is the integral over this plus the integral over this, if I'm going all the way around, is just the same as the integral over the boundary. So what happens here is when I have all of these little squares, all the interior sides cancel. And what's left over is I have the area integrals over each one of these pieces is then equal to the line integral over the boundary. And what happens? Well, the rectangles keep moving closer and closer and closer to the boundary over here. And then all you need to do, and this is where some analysis is required, is you replace any part of the curve here with like a little polygonal path like this. And now once you do that, now you can just keep using your rectangles and your squares. So this is the part of the proof where you have to really roll up your sleeves and do some careful bookkeeping as to what happens as you look at the curves of the arcs. But the idea is, and you've got to be a little careful, as long as I have something like this and I have an arc like this, the integral over the line segments should be very close to the integral over the arc, and in the limit they should be the same. It's enough to do Green's theorem for a square or a rectangle because when you have them next to each other, the interior sides cancel. If I had something down here, you then see that the horizontal side would cancel. And so all the interior sides cancel, and you're just left with the integral over the boundary. All right, we did a little bit better than the 10 o'clock section. We have a minute and a half to spare, not 30 seconds. So we have a little bit more time for a brief summary. All right, we did a lot today. This is normally 2 weeks of material. All right, the only way to do it in one day is to go fast. But this leaves us more time in the semester to talk about applications of multivariable calculus. And since most of you are never going to use Green's theorem again, I think it's better to do applications than to spend 2 weeks on a theorem you're never going to use. Why was it worth the day? Well, as I said earlier, when I die and go to mathematical heaven, as I expect to, I will be able to proudly tell people, yes, my Calc 3 students have seen Green's theorem. If by some chance you are faced with the pearly gates of mathematical heaven, you can say that too. But more importantly, as we did all this stuff today, we reviewed a lot of the concepts from Calc 3, and we saw where they go. Okay, so we still have another 40 seconds to summarize, right? We got to see the mean value theorem all over the place. When you want to look and see how much you've changed by, the mean value theorem is a great way to quantify how much you've changed. We saw Riemann sums again, or a generalization of Riemann sums, that you chop things up and then you take some kind of limiting process. Most importantly, I think, of everything we did today was the concept of a line integral, integrating a vector over a curve and getting a number. There are lots of different ways to try to define the integral of a vector field, a vector valued function over a curve. Why was this a good choice? Well, the curve has a unique tangent at every point. It doesn't have a unique normal. It suggests that this is the right thing to study. Green's theorem is a massive generalization of the fundamental theorem of calculus, and it's relating the derivative of a function over a region to the integral of the function over the derivative of the region, the boundary. That's really how you should view the fundamental theorem of calculus. Okay, so this was an impressive day. If people can stand up afterwards, that's a good sign. If you haven't turned in the last homework assignment, please do so. Pick up solutions.